Okay, so good evening, everyone. Thank you for sticking to this late hour. I'll be talking about concurrency in C++ memory model. Some of these slides I've stolen from other people, very famous people, so I apologize to them in advance. Hope they don't sue me. So my name is Pavel. Let's see if this actually works. My name is Pavel. I'm a developer, trainer, author, and apparently speaker, so speaking. I've written a few books, and they're available on Amazon. Please buy them, and they make me money, so go ahead and do it. I'm an MVP, at least for the next 3 days. I have some courses on Plural site, which you can also watch, and that also brings me money, so again, motivation for you. I have a blog you can read if you don't have trouble sleeping. Some people helps them actually. I have a few tools on GitHub which you can look at, most related to Windows internals, because I wrote the book, so I have to kind of maintain some facade. But for this session, I'm going to talk about C++ concurrency a little bit and the C++ memory model, which is actually pretty scary. But hopefully it will give you some sense or some idea of what's going on in that arena. There have been several sessions of that on various conferences, but I want to give you my take on this. So first, we have several standards today, and we know that we are C++ 17. C++ 20 is kind of coming along pretty quickly, and C++ had that hole between 98 and 2011, where nothing was really going on within the standard, or at least not much. So when C++ 11 came along, then stuff started exploding in all areas of C++. So for example, in C++ 98, the word thread is not mentioned. So nobody actually wrote threads in C++ 98. We know that. All programs were just single-threaded. Well, probably not. But every compiler did whatever it wanted to do. There was no standard behavior. There were many various types of libraries like TBP and Boost stuff and OpenMP and whatever to do multi-threading in various ways. And now finally in C++ 11, we have the word thread actually represented several times, and we have something called the memory model, which really describes what are the rules for accessing memory between multiple threads, what we should expect from these kinds of behavior. And of course, there are enhancements in C++ 14, 17, and 20 in that regard. So, what do we want to do? Any concurrency? Concurrency is really running some stuff in parallel. This is basically concurrency, doing things concurrently. So there are actually basically just two reasons. The first one is to maximize performance. We're in a multicolor area with many CPUs, and there are GPUs that want to leave them out of this session. And so we want to maximize our performance. And people that are writing in C++ typically care about performance, at least to some extent. The other reason is just for design purposes. So if you take any reason you can think of about why you want to do things concurrently, it will fall in one of these categories. All the other things you can actually put in the second category if you don't care much about performance. It's just about how you design your code, how you structure it, and so it gives you some benefits. So we need to design for concurrency. It's not something you want to do later. Let me run or write everything in one thread, and then we'll add some stuff to do concurrently to make things better. That typically will not work. So you should always design that up front and take the appropriate consideration to that, because you may introduce a lot of new and subtle bugs, which I'm not sure the zoology session previously can actually help you decipher. So you should probably think about this beforehand. So a brief overview of what's going on in the hardware level. So we have today the idea of a socket, which has a set of cores, and each core sometimes is split into two hyper-threaded threads, which is an Intel technology which also exists on AMD processors and other vendors. So you have several logical threads within the same core, and they are not completely independent. They share some state, especially some levels of caching, as we'll see in a moment. So we have a set of logical processors on the system which we want to utilize as much as possible, at least if you care about performance. So here's a simple example to kind of start you up. We have a very simple algorithm here which what it does is, you can probably guess, it sums up a matrix. So I have a class here called a matrix. I've written that class, and it has appropriate operators for the index operators, to get an element in a particular location. And I want to sum these values in two ways. So these are two ways which are essentially the same. And we're just exchanging what the rows for columns. So we're doing row major summation, and then we're doing column major summation. We want to see what's better. And if you studied any computer science, you would say, I mean, that's exactly the same thing. We're doing exactly the same work. I mean, what's the difference? It just seems pointless. But unfortunately, all this stuff related to performance, in many cases, our intuition is blatantly wrong. I mean, just miss the point. We think something that seems to be making sense, but eventually find out the reality is completely different. And so in these cases, we always talk about performance. First, you need to measure. You can't predict anything, and even your strongest intuition may be completely wrong. So in this case, it looks like this should be exactly the same, but in fact, it's very much not so. So here's a little benchmark I did on my machine. This is not my machine. I don't go with no forever, but I did it with this machine. And so with this particular type of processor, and with a Visual Studio 2017 15.6 compiler, which is fairly recent. And as you can see, I've used several sizes matrices to check this out. One was with row major, and the other with column major, and I measured the time it took and also the sum of these numbers just to make sure I'm actually getting the correct result and doing the same work. As you can see, the results are the same, but from timing purposes, this is completely different. Row major is much faster than a column major. And that's because we have the idea of caches. So caches are really a fundamental part in computer architecture today and the way CPUs work. Because in the distant past, the speed of processors was comparable to that of memory. And so it was kind of fine. But later, we see a lot of digression, and so memory is much, much slower than CPU. And so if the CPU would communicate directly with memory, what we get is CPU stalling almost all the time and not getting any work done. Its high frequency would be completely wasted. And so we need a cache. The purpose of the cache is to provide fast memory for the CPU. And so if you can make your needed memory reside mostly in cache, you get better performance. If you have to actually go to memory, you'll get worse performance, and I mean really worse performance. So the idea is you want to utilize the cache as much as possible. So this is what we have in a typical computer system. I mean, typical laptop, for example. We have several caches. Each cache has a level. Level really means its distance from the processor. The closest to the processor, the cache is faster but smaller. And the numbers we're talking about here are very, very small. And the reason why we got different performance is that because things are, when they are consecutive, contiguous in memory, they can be brought together into the cache, and then the CPU just goes over the cache, which is much, much faster. In the column major case, we did just kind of jumping to other location within memory, which we missed the cache because the cache is small. And then we had to kind of get the data from real memory, which is several times factors slower. And that's why we get these differences, which again, computer science says everything should be exactly the same. So performance is not just about multi-threading or multi-cores. You need to always look at some other things which are not obvious. In this case, this is cache. So here are some typical sizes for caches. They are really, really small. I mean, 32 kilobytes. You remember what a kilobyte is anyway? I mean, I don't really know what that is. You take a telephone, you have more memory than I had in all my Commodore 64 computers ever. I mean, this is really, really small amount of memory. And in fact, the way caches work, they don't work on single bytes. They work on something called a cache line, which is typically 64 bytes in size. So even if you write a single byte, you don't actually write a single byte. The processor is actually going to write more than that. whether you want it or not. This is just part of the optimizations that the CPU hopes to make depending on the code that you write and the way you arrange your memory. And so here's another example for you. This is a little bit more tricky. So I'm going to describe what we see here. The idea is very simple. We have an array of numbers. We want to count the number of even numbers in that array. And because this is something we can actually split into multiple threads, we want to do it. We want to split it into multiple threads and see if we can get better performance by using multiple threads where each thread will take a chunk of the data and then just count its own even numbers in its own chunk, and then finally we'll just sum everything up and see what we get. And so let me describe the code. If you haven't seen multi-threading in C++ 11, let me give you a brief overview here. So we have the function called the count even numbers, that's version 1, and it has the pointer to the array, the size of the array, and the number of threads we actually want to use, the amount of concurrency we want to introduce into the algorithm. What we do here, I create here an array of numbers which should hold these counts for that I'm trying to do here. So each one represents count provided or updated by a particular thread. And then what we do, we try to create n threads, and each one has a start and end point, which is the chunk that was allocated for that thread. In this case, the last thread gets to get the rest of the tail of the chunk that just wasn't divided properly, which is of course not that very important for our purposes. And so I'm creating a thread here. Here's the thread object, and I'm passing in a callable object, in this case a lambda function. And I'm saying here's you get your start. Here's your index in the table of counts, of sums, where you need to put your own sum, which belongs to you, which is part of this array. Here's your starting index, here's your end index, and just go for it. And so what we have here is just running over a simple loop and incrementing the counter in the appropriate index if the actual number is in fact even. Very, very simple. And we pass these parameters to the lambda function, and then we just add these to the array, the vector of threads here. We need to do move because thread is not copyable. You can't just copy a thread. What would that mean anyway? That doesn't really compile, so we need to move the ownership from the T object, kind of making it a zombie, and putting it into the vector of threads. And now these threads start executing immediately. Once you create an object, just starts executing. And so all the main thread needs to do here is just wait for them to finish by calling join on the vector or each thread inside the vector. And once they're done, it's going to just sum up all the parameters of that array, and then we get the final result of the sum. So this is the idea. And let's see how it fares out. So I tried that with from 1 to 8 threads. Because this machine had 8 logical processors, so it kind of makes sense not use more than 8 processors, because then it would be context switches and contention, stuff like that, and I don't want that to happen. So I used 1 thread, then 2, then 3, and counted I got the sum and made sure it's exactly the same value, and then how much time it took. And if you look at the results, which may be a bit small for some of you out there, we can see that the first thread does the worst, but the performance improves somewhat, and then it starts to get worse. So adding more threads, but it starts to get worse, which is really, really weird. We actually expect some form of linear improvement, because each chunk is equal in size practically, so each thread is doing the same amount of work. So everyone should be working all the time. There's no such case when one thread finishes early, and so there's an empty processor just sitting there. So we should have improvements, but we don't. Anybody knows why? Except I did maybe saw my presentation.
Thread creation.
What, creating what? Threads? No. Why? There's no overhead for that, because I'm creating only 8 threads at most. That's it. Creation is not that bad. Most of the time is spent working that loop.
What is the difference between each chunk?
Between what?
Each chunk, what is its size?
I don't remember, but big.
You're fighting over the
Right. So some of you know all this stuff, probably you've seen that previously. They're fighting over the cache. So what we have here is something called force sharing. Because here's what happens. Every thread goes to its own index. So it is a different memory location, so there's no data race here. So there's no problem. The algorithm works. So the standard, one of the promises of the standard is saying if you access different memory locations by different threads, you're okay. Everything should work out just fine. So theoretically, I'm fine. The sums are all correct. But what we have here, because these counters are contiguous in memory, they would typically fall in the same cache line. So once one thread is writing there, it actually invalidates that cache line. So the next one does it and validates cache line again. So we have reads from memory rather than working with the cache alone. And this is really a major bummer in this particular case. And so all we need to do is make simple change by introducing a local counter for each thread and adding, just incrementing that counter, that local counter, and putting the result in the final index only once. And the results are really improved significantly. Even the single thread case is much better now because the chance of these locals falling adjacent to one another in memory is really, really slim because they're part of a stack, and stacks are typically enough far apart so they don't fall in the same cache line. And so we do get an improvement each time we add more and more threads, which is what we expect. So what we got here was force sharing. We actually were sharing a cache line which we didn't maybe miss them. And so this is again something to look at. Again, theory is one thing, reality is different. So this just gives you a sense of what we actually need to deal with generally. And once we are past this sort of introduction, let's go and start discussing the memory model, what's going on in C++. So here's a simple example, and the idea here is that I want one thread to provide some data and then signal another thread to pick it up. Say the data is ready. So thread number 2 here, this T2 thread, prepares some data, which in this case is just a simple assignment to A, and then signals using this flag that the data is ready. And then the other thread is waiting for this flag to become true, and once it does, it takes the value from A and puts it into B, and that would be the final result. Very, very simple case. Now, what do we expect the result to be? Should it be 5 or maybe 0? And again, if we look in computer science and maybe common sense, it should be 5. Putting 5 here, setting the flag, so then the loop is aborted and taking the flag, that's fine. However, that's not really necessarily the case. It may be the case, but may not be the case. In some cases, we get 0. That's because there are optimizations that the compiler or the hardware can make and reorder these two instructions. They are allowed to do it because they're independent. So from the compiler's point of view, and if the compiler doesn't do it, the hardware may do it. And so in some cases, flag will be 1 immediately, and only then A will be 5, because from the compiler's point of view, the compiler never looks at other threads. It has no idea what to do with that anyway. It only looks at a single thread of execution from its perspective, and so it says maybe it's better to set flag to 1 because, and I'm not talking, when I'm saying compiler, what I really mean is compiler and everything underneath, which means whatever runtime is there, the hardware, whatever. It doesn't really matter at what point the optimization is applied. It doesn't really matter. We don't care, and it doesn't matter for the final result. And so the hardware may say, hey, I actually accessed flag or something close to flag in the cache line previously, so maybe it's better to access it right now and then go to access A because that's in a different location. So this can happen. It happens. And so this is something that is called in C++ and C++ standard and generally a data race. A data race is the case where two or more threads access the same memory location, where at least one of them is a writer, which wants to make changes. Everyone is reading, that's fine. If anyone wants to make changes, then all hell breaks loose. And we need to have a memory model describing what the result should be in these cases. So here are some basic definitions. Question?
Volatile doesn't like memory?
No, it doesn't. It doesn't. So volatile here actually, volatile is actually different than, it doesn't provide any memory barrier. Volatile is something I actually have on my second to last slide before the Q&A. So we'll probably get to it. Maybe we'll get to it. So I will say that volatile is something that just says to the compiler and hardware, you can never optimize this variable. It's not the same as volatile in Java, for instance, which does means memory barrier. It is unrelated to concurrency at all, because the idea there is that it may be changed from an async operations made by hardware, for instance, like interrupt and stuff like that, and there's no way to know. In fact, even if you have a code such as, let's say we have a volatile, and I'm saying my volatile equals 1, and then I have something like a equals the volatile, the compiler cannot change that to a equals 1. It cannot do constant propagation. It can't do that because it knows nothing about this variable and will always read it. The reason I put here volatile is what? Because of that Y thingy. Because the compiler would say, hey, you're checking flag, you're not doing anything to it in the loop, so I just read it once and I have an infinite loop here. So I'm just forcing, in this case, the compiler not to make that optimization. That's the only reason I added volatile here, but it has nothing to do with concurrency at all. And in fact, it is out of the C++ memory model. So, some basic definitions. We have byte, which is probably something you're aware of. Memory location is where objects are stored and everything has a distinct memory location except bit fields, which are, in case they don't share another byte boundary, they have the same address. So this is something to keep in mind in some cases. We have an independent control flow, which we call a thread, and we have something called a data race, which I just mentioned. Data races are the problematic things in concurrent code. We have multiple threads accessing the same memory, in which at least one of the threads is a writer. So here's another example to show you the problematic stuff. This is a very well-known algorithm from the 60s or something like that, maybe 70s, from Decker. And this is kind of a poor man's critical section. So the idea is that I want a single thread between these two threads to enter some critical region of code where it may be accessing some shared data. So here's one conceptual way to do it. When I want to be the one entering the critical section, I'm setting flag 1 to 1. This is my signifying my intention to enter the critical region. And then I'm checking the other guy's flag. If it's true, it means it said that already, I'm going to back off because it would be the one entering the critical region. If not, then I'll be continuing into my critical region, and my friend there is going to do the exact opposite. In theory, again, this is something that works. But in practice, it is possible both threads enter the critical region. And there are several reasons for that. One of them is reordering. But even if we disregard reordering, say, hey, that will not be reordered. There's something else in play here, which is something called a store buffer. So the idea here is when we set some value, the CPU doesn't really come running and writes that immediately to memory. That's way too slow. It's going to write it to something called a store buffer and then flash that store buffer asynchronously later without hanging on to the processor, the processing power, and letting the thread continue on its merry way before even that happens. And so one flag sets the value 1 to flag 1 in the store buffer. Same goes, for example, practically maybe the same time, another processor from flag 2. And when the first thread tries to read the value of flag 2, because these are and not the same locations, it goes into main memory. And so it doesn't see the updated value. Why would it? There's no reason. Nobody told it they're actually needed to be synchronized. We have to do something to make that work, because that actually requires the hardware to work harder. And so by default, we just get the value 0 for main memory, because again, there's different locations. If we try to read flag 1, we'll get the correct value of 1, because it looks at the store buffer first. But the store buffer doesn't have anything to do with flag 2, so it goes to main memory. And so what we get here is just missing the point, and it doesn't work even if there is no reordering in the original algorithm with flag 1 and flag 2. So that's not good. We need to do something about it. And this is something we aspire to, called sequential consistency. Sequential consistency means that the program executes in a set of steps which you can reason about, which you expect, even if multiple threads are involved, and you actually get the behavior you kind of expect to be. However, sequential consistency has a price, and that price is reducing the optimizations possible to do by compiler and hardware. So here's an example of what sequential consistency means. Let's say we have two threads, T1 and T2. T1 does A and then does B, T2 does C and then does D. So sequential consistency means that all of the combinations are possible between these operations while maintaining order. So for example, this is a legal case. This is a legal case as well. I can reason about it. I know that can happen. This is a reasonable case as well. And so is this one. And so is this one. However, something like this is not possible in sequential consistent code, because we have something that is out of order, maybe even running completely concurrently with another thread. So of course, in practice, this also may run concurrently, but the effects seem like they aren't running concurrently. That's what sequential consistency means.